Hi, good morning, everyone. How are you? How is life? Good. What is shape? You're still good. Always think it's good, then it will be good. Okay, be positive. I'm serious. Do you know about it? I know, man. If I start talking about it, it will be out of physics. So let's start the topic for the day. What is the last subtopic we have done? Come again. We started with magnetic field, and we spoke about force acting on a conductor when it is kept in a magnetic field. So guys, I told you this is something that you had done for your O-levels. You know when a conductor is carrying a current and when it is kept in a magnetic field, it will experience a force. Okay, correct? That happens when the conductor is perpendicular to the magnetic field. Okay, so when the conductor is carrying a current in the magnetic field, and if it is kept perpendicular to the magnetic field, it will experience a force. And the direction of that force is given by Fleming's left hand rule. That is something that we have done by your O-levels. Correct? Fleming's left hand rule. Yes. I haven't done that bit. So the magnitude of the force acting on the conductor, is given by this equation we discussed last class. F equals BIL, right? Where B is the magnetic field strength, I is the current, L is the length of the conductor. This is when the conductor is kept perpendicular to the magnetic field. Okay. And then I told you, if the conductor is not perpendicular to the magnetic field, you have to take the perpendicular component of the magnetic field strength to use in this equation. So for an example, if the angle between the conductor and the magnetic field is I, if this is I, okay, and if this strength of the magnetic field is B, the perpendicular component of the magnetic field perpendicular to the conductor will be, this component will be B sine theta. Okay, so the equation will become F equals BIL, where the B is now B sine theta, B sine theta into IL. So the equation becomes BIL sine theta. So if the conductor is not perpendicular to the magnetic field, the force acting on the conductor is given by F equals BIL sine theta, where theta is the angle between the conductor and the magnetic field. Is that okay? Right. So we are supposed to continue from here to there. Did you also mention that the direction is given by Fleming's left hand? No. Right under that. The direction of the force acting on the conductor. The direction of the force acting on a conductor. The direction of the force acting on a conductor in a magnetic field. In a magnetic field. Is given by Fleming's left hand rule. Is given by Fleming's left hand rule. Right. So guys, Fleming's left hand rule says what? Listen. If you arrange the first three fingers of the left hand perpendicular to each other, the thumb, the first finger, and the second finger. Okay, don't follow the middle finger. thumb, first finger, and the second finger. If you arrange them perpendicular to each other, when the first finger is indicating the direction of, okay, it's easier to remember this way. FBI. FBI. F stands for force. B stands for magnetic field. I stands for current. FBI. FBI. So if the first finger is indicating the direction of the magnetic field, and if the second finger is indicating the direction of the current, then the thumb will give you the direction of the force acting on that conductor. Is that okay? That's what Fleming's left-hand rule says.
Okay. So according to your diagram, it's the force is acting downwards, right?
According to which diagram we are talking about?
The first one. This one.
This one.
Yeah.
D is this way, I is this way. Yeah, force is into the plane of the paper. In this case, D is this way, I is this way. Force will be into the plane of the paper. D is this way, B is this way, I is this way. So the force is into the plane of the paper. Right? Fine. Right under that, the subtopic. Fleming's left-hand rule. Thank you. I'm an artist. Right on that. When the first three fingers of the left hand are arranged perpendicular to each other. When the first three fingers of the left hand are arranged perpendicular to each other. Come on. Thumb gives the direction of the force. Thumb gives the direction of the force. When the first finger gives the direction of the magnetic field, thumb gives the direction of the force. When the first finger gives the direction of the magnetic field, and the second finger gives the direction of the current. Okay, right. So guys, let's look at a few examples how to apply this rule. Okay, look at this first example. What are these processes? What does that mean? This process here means the magnetic field is into the plane of the paper. So guys, the magnetic field is into the plane of the paper. The current is to the right, which way will be the force. Arrange the fingers.
Upwards.
B is into the plane of the paper. The current is this way. Force will be upwards. Magnetic field is into the plane of the paper. Current is this way. So the thumb is upwards. Okay. Magnetic field is in. So this finger is magnetic field. Current is to the right. Thumb is directed upwards. Okay. Guys online, just hold your paper like this. Okay. Magnetic field is into the plane of the paper. The current is this way. So the thumb is pointed upwards. So the force is upwards. Okay. Right. Take it down. As mentioned about the key, the process here means magnetic field is into the paper. Yeah. Right. Let's try the next example as well. Now the magnetic part B. Magnetic field is into the plane. The current is up. Decide which way the force is going to be. Yes.
Towards the left.
So magnetic field is in, current is this way. So the force will be to the left. Okay. Right. Do you understand how to use Fleming's left hand? Let's try another one. Part C. Let's say part C. Magnetic field is into the plane of the paper. The current is to the left. Which way will be the force? Right? So guys, now the magnetic field is in, current is this way, so the force is downwards. Is it? Yes? Okay.
Sir, can we put upwards also?
No. How? Arrange the fingers and so here. The magnetic field is this way. Current is this way. Thumb has to be pointed down. There can't be two directions. Okay. Bro, left hand, bro, left hand. Left hand. Guys, let's try another one, part D. Now here, for the magnetic field, I have put sorry, a dot and a small circle. What does that mean?
Out of the page. Magnetic field out of the
Not process. The magnetic field is out of the plane of the paper. This notation means the magnetic field is out of the plane of the paper. Okay. Can you tell me in this case, which way will be the force? B is this way, I is this way,
downward.
downwards. Force is downwards. And take down that notation, that dot and circle mean the magnetic field is out of the plane of the paper. Right. Guys, do you know what? What? I challenge Fleming. Do you know that? Yeah. I challenge Fleming. When Fleming came up with his left hand rule, I came up with my right hand.
So don't lie, sir. There is the right hand rule, Mr. Before.
Not special challenge.
It was Fleming's left hand rule. So
So there is Fleming's right hand rule also, sir.
that is Fleming's right hand rule is different for a different purpose. I'm talking about in this case, to find the direction of the force, I have my own rule. You want to know? Listen. Guys, now this I call it my slap rule. What do you call it? My slap rule. Listen carefully. If you have your right hand in this position with the palm open, okay, and these fingers will be, the thumb should be perpendicular to the remaining fingers. Okay. Listen. In this case, when the thumb is indicating the direction of the current, okay, and the remaining fingers are indicating the direction of the magnetic field, the direction of the palm gives the direction of the force. Like you slap someone, you give the force with the palm, right? So it's easier to remember this is the force. The single finger, thumb is the direction of the current. The remaining fingers are the direction of the magnetic field. This will 100% work. And this is easier to use. Go back to the first example. Okay. Current is this way, magnetic field is this way, force is this way. Second example, current is this way, magnetic field is this way, force is this way. Okay. Third example, magnetic field is this way, current is this way, force is this way. The fourth example, magnetic field is this way, current is this way, force is this way. Okay. So, I mean, this is something you can't write, but you can use. You can write at the exam if they ask which law you use to find the direction of the force.
No,
You
sir,
have to
Fleming's
tell
left hand rule is easier.
we use what did you tell you, sir?
So Fleming's left hand rule is much easier, sir.
Okay. Okay. You can use whatever you want on one of the two, but you have to tell that you use Fleming's left hand. Right. Can you take down this as well? Part E and F.
So upwards and then right.
Yeah. In part E, because the magnetic field is out, current is to the left, force will be upwards. Agreed? Force will be upwards. In part F, magnetic field is out, current is to the up, force is to the right. Yes or no? Is that okay? Tell me about this one. G. Current is up, magnetic field is to the right. Which way will be the force? Into the paper, into the plane of the paper. Am I right? Part H, current is down, magnetic field is to the right. Which way is the force? Out of the plane of the paper. So in G and H, you will not be able to mark the direction, but you can write the answer in words. So guys, mention in G, the force is into the plane of the paper. In H, force is out of the plane of the paper. Sorry. B is the magnetic field. Usually B is denoted to represent the magnetic field strength. Magnetic field strength is denoted by B. So that's what we use here for magnetic field. Right. Guys, write down a question. A conductor of length 50 centimeters. A conductor of length 50 centimeters carries a current of 200 milliamperes. 200 milliamperes. Perpendicular to a magnetic field. The conductor of length 50 centimeters carries a current of 200 milliamperes perpendicular to a magnetic field of flux density 50 millitesla. 50 millitesla, full stop. Calculate the force acting on it. Okay. The force acting on it. Okay. What is your answer? So just use F equals BI here. B is 50 millitesla, so it will be 15 to 10 to the power minus 3. I is 200 milliamperes, which is 200 into 10 to the power minus 3. The L is 50 centimeters, which is 0.5 in meters. So it's 5 into 10 to the power minus 3 newtons, is it? Yes. Right. Right on the next one.
So once again, sir, can you go back, please? I didn't finish writing the question. Okay, Siddharth.
Right, we'll start on the next question. A conductor of length 80 centimeters. The conductor of length 80 centimeters carries a current of 2 amperes. Carries a current of 2 amperes. At an angle of 50 degrees to a magnetic field. 50 degrees to a magnetic field. Degrees to a magnetic field of flux density 500 microtesla. 500 microtesla. Full stop. Calculate the force acting on it. 10 to the power minus 6. 1 micro means 10 to the power minus 6. What's the answer, guys? So it's F equals BIL sine theta. B is 500 into 10 to the power minus 6. I is 2 into L is 80 centimeters is 0.8 meters. Sine theta is 50 degrees. 6.13 into 10 to the power minus 4 newtons. Is it? People online are getting this answer.
Yes, sir.
Right. Then guys from the queue. Question number 14. Give it a try. Give it a try. Done? Done? Right, okay. Guys, in 1821, Michael Faraday made what is believed to be the first electric motor. The stiff wire was suspended freely from a stand. The mercury completed an electrical circuit which included the wire. When there was a current in the wire moved around the magnet. The wire made 10 complete revolutions around the magnet in a time of 8.3 seconds. Calculate the angular velocity of the wire. So guys, angular velocity, I can take it as angular displacement over time. One revolution, one turn is 2 pi radians. Correct? So 10 revolutions made means it's 10 into 2 pi will be the angular displacement made. Over the time taken is 8.3 seconds, which is 7.57 radians per second. This is easy marks. Sorry? Same thing. 7.57 radians per second. This I would consider to be the easiest 3 marks of the paper. Part B, when the current in the wire is 1.1 amperes, the wire is at an angle of 10 degrees to the vertical. The length of the wire in the horizontal, magnetic field is 3.5 centimeters. Determine the force on the wire. Magnetic flux density is 0.053 Tesla. Right, guys, don't write, just look at the screen. So F equals BIL sine theta. D is 0.053. I is 1.1. Into L is 3.5 centimeters, means 3.5 over 100 in meters. Into sine 10. Did you do this? Who did this? Who did this?
So that's wrong, sir. It should be cos 10, sir.
We have done this, mark it wrong. Yeah. Now here what is given as 10 is not the angle between the magnetic field and the current. They have given this as the 10. If that is the 10, the angle between the magnetic field and the current is supposed to be this one, which is 80 degrees. So then your angle here should be BIL sine 80 degrees or cos 10. Cos 10 is the same as sine 80. Okay. So be alert. If you have done this, you will get the right answer. Okay. So it will be (2.01).
Yeah, 2.01 into 10 to the power minus 3 newtons.
10 to the power minus 3 newtons.
And the force will be out of the plane of paper.
Direction of the force on the wire. Fleming's left hand rule. So guys, now the perpendicular component of the magnetic field, current, you can look at this. Current is this way. The perpendicular component of the magnetic field is this one. That is this way. Correct? This is a magnetic field. The perpendicular component of the magnetic field. That's what matters. So now the B is this way. B is this way, I is this way, force is out of the plane of the paper. B is this way, I is this way. Force is out of the plane of the paper. So the direction of the force on the wire, out of the plane, out of the wire. No, that doesn't specify the direction. Out of the plane. that says, okay, outwards should be that you can agree on that outwards. So I would mention out of the plane to be on the safe side. Okay. Right, because then right on the next subtopic. Path of a charged particle in a magnetic field. Path of a charged particle in a magnetic field. Okay, where's now? Look at the screen. Now let's say there is a magnetic field, listen to me carefully, which is into the plane of the paper. Okay. And there is a positively charged particle entering into this plane the way it is shown in the diagram to the right. And let's say it has a charge of positive Q and entering at a speed of V. Okay. So its direction is supposed to be this way. If there is no disturbance by the magnetic field, it's supposed to be moving that way. Correct? So guys, the rate of flow of charge is what we consider to be the current. A charge is moving means, that means it's a current flow. Correct? So the direction in a positive charge moves is what we consider to be the direction of the current as well. So when this positive charge is moving this way, that is equivalent to a current flowing in this direction. Correct? So now this moving charge will experience a force in this magnetic field. Okay? And to see which way the force is going to be, once again we can use Fleming's left hand rule. Same way, Fleming's left hand rule we can use to find the direction of the force. So guys, now the magnetic field is into the plane of the paper. The current is that way, which will be the force? Upwards. So there will be a force on this fellow. Force on this fellow this way. As it enters, the force will be to the right. Force will be up. Correct? So then, will it go straight? No. It will start bending and it will have a circular path inside the magnetic field. Understood? It will have a circular path. The reason why it will have a circular path is this force due to the magnetic field at any point on this path, let's say the particle came to this point, then the force will be this way, perpendicular to the direction of the current. This will be a circular motion. So this magnetic force will provide the centripetal force which is required for the particle to be moving in a circular path. Understood? So the path of a charged particle in a magnetic field will be circular. Is that clear? Right.
So what is the V rho, sir?
V is the speed. V is the speed at which it's moving. Speed or velocity.
But that's not the exact same thing.
Yeah, but here the V you can consider to be the speed. Okay.
Doesn't matter whether it's a plus or minus charge, it's still the same.
No, it will matter. I will explain.
Still, it is a centrifugal force, but the mechanism is very different.
The direction will be different. Now this I have given for a positive charge. I will explain how it works for a negative charge as well. Just take it back. Okay, right. Guys, make a note under that. When a charged particle enters into a magnetic field, when a charged particle enters into a magnetic field, when a charged particle enters into a magnetic field perpendicular to the field, perpendicular to the field, comma, it will experience a force. It will experience a force perpendicular to its path, perpendicular to its path, and it will move in a circular path. And it will move in a circular path. Full stop. The direction of the force, the direction of the force is given by Fleming's left-hand rule. Fleming's left-hand rule. Full stop. The magnitude of the force is given by the magnitude of the force is given by F equals BQV. So guys, take down this equation. This is the force acting on a conductor in a magnetic field which is moving at a speed v, where the strength of the magnetic field is B and the charge of the particle is Q. Guys, write your names and pass it around. F equals BQV. right? Actually, based on that, you can derive this one, but not necessarily. Mm. Q equals IT and V equals L over T, then the T is the same thing. F equals BQE, right? Fine. Guys, now look at this. Now, that is I just told. If the particle enters perpendicular to the magnetic field. Now, if the particle enters not perpendicular to the magnetic field, and if it is entering at an angle theta, now let's say the magnetic field is this way, B, and the particle, the positively charged particle enters this way at an angle theta, then the equation will be, you have to consider the perpendicular component of the magnetic field once again, which is B sine theta. Okay, so then the equation of the force will be F equals B sine theta into QV, which will be BQE sine theta. Take down that as well. When the particle is not perpendicular to the magnetic field. Okay, BQE sine theta. Right. Guys, write down a question. An electron beam travels across a an electron beam travels across a 36 millitesla magnetic field a 36 millitesla magnetic field at 45 degrees to the field. At 45 degrees to the field. Full stop. If the electrons are traveling at 10% of the speed of the light, if electrons are traveling at 10% of speed of light, come on, what force does the field exert on each electron? What force does the field exert on each electron? Right? For your information, the speed of light is 3 into 10 to the power 8 meters per second, and the charge of an electron is 1.6 into 10 to the power minus 19 coulombs. Give it a try. Charge of an electron is 1.6 into 10 to the power minus 19. What is your answer? So guys, F equals BQE sine theta. BQE sine theta. The B is 36 millitesla, which is 36 into 10 to the power minus 3 Tesla. Q is the charge of the electron, which is 1.6 into 10 to the power minus 19. V is 10% of the speed of light. Speed of light, 3 into 10 to the power 8. That into 10% is, that is,
7, sir.
sorry?
10 to the power 7.
Yeah. Into sine 45.
So 1.222 multiplied 10 to the power minus 3.
What is the value? 1.22 into 10 to the power 13 minus 13 newtons. Is everyone getting this answer? Yes.
So it is 1.2218, so I wrote 1.22232s.
Right, guys, write down the next subtopic. Radius of the circular path. Radius of the circular path of a charged particle in a magnetic field. Guys, draw this diagram again. Did everyone write the name? Okay. Right. Now, guys, a charged particle, when it enters a magnetic field, it has a circular path. So I'm going to come up with an equation for the radius of this. Okay. Now, I'm going to use F equals ma for this particle, which is moving in the circular path. Okay. F equals ma. So F is given by B, Q, V. Right? M into A is given by V square over centripetal acceleration. So one of these V's will cancel off with this V. BQ equals MV over R. So if you get the R subjective, R equals MV over BQ. Okay. What is M into V? Momentum, mass into speed. So you can also take it as R equals P over BQ. And this is how it is derived. Is that okay? Yes. Take it down. Zoom it. Okay. Right, okay. Guys, write down the next subtopic. EMF induced in a coil. EMF induced in a coil. Right. Yeah, before that, there are a few questions we can try from the tube. Guys, take the tube. Question number 4. Question number 4. Page number 8. In 1897, J.J. Thomson demonstrated that electrons are small negative particles. The diagram shows the apparatus used by Thomson. Okay. A potential difference V was applied across the metal plates, producing an electric field between them. A magnetic field of flux density B was applied at right angles to the field. Electrons were emitted from the cathode. Electrons were emitted from the cathode and accelerated towards the anode. The electrons moved between the metal plates with a speed V. Thomson adjusted the B until the electric and magnetic forces on the electrons were equal and opposite, so that the electrons pass between the metal plates in a straight line. The plates are separated by a distance d. Show that the speed V of the electrons is given by this. Guys, I have understood the question. Can you please read it again? I will do it, but read the question properly. Okay. Right. Let me explain you what is told in the question and what Thomson has tried to do. Listen. So guys, there is a cathode here which is negatively charged and there is an anode here which is positively charged. So the electrons are negatively charged. So what will happen? Definitely they will accelerate towards the anode. Okay. So he has changed the potential difference between the cathode and anode to the value whatever he wants, to give whatever the acceleration he wants to give it to the electrons. So what happened? These electrons got a speed and they entered and they moved into this metal plate, between the metal plates with a speed v. Let's say with a speed v. Okay. Speed is v. Now, these metal plates, one is a positively charged plate and the other one is a negative, because they say there is an electric field between the metal plates. So one is a positively charged plate and one is a negatively charged plate. So then what happens by default, this negatively charged electron will try to get attracted to the positive plate and it will try to bend towards the positive plate. Correct? That would have been the case if there was only an electric field, right? So what did Thomson do? He also put a magnetic field here in such a way the force due to the electric field on the electron will be in one direction. Okay, force due to the electric field is, let's say, this way. He put the magnetic field in such a way the force due to the magnetic field is in the opposite direction. And also he made sure these two forces are equal in magnitude. Okay, so he has chosen the magnetic field strength in such a way the force due to the electric field and force due to the magnetic field will be exactly in opposite direction. They will be exactly equal in magnitude. Correct? So then what will happen? What will happen? What will happen? This electron will just continue straight without any deviation. Am I right? That is what they have explained in the question. Okay. If you want, read it again and see. That is what they have told in the question. Fine. The question is now, the plates are separated by a distance d. Show that the speed v of the electrons is given by v equals v over vd. Right. There's the electric field strength. Electric field strength between the plates is given by v over d. Potential difference between the plates divided by the distance between them. Okay. For a parallel plate, the electric field strength between them is given by v over d.
So how did you get that formula?
It's electric field strength is equal to potential difference between in a capacitors. Electric field strength is equal to the potential difference between the distance, right? So v over d. So the force due to the electric field will be if V equals E into Q, electric field strength into charge. Agree? So force due to the electric field, if E will be V over D into Q. Am I right? Electric field strength is V over D. Charge is Q. So it's V over D into Q will be the force due to the electric field. On the other side, force due to the magnetic field will be B, Q, V. Now here guys, there are two V's. The capital V is the potential difference. Simple V is the speed of the particle. Okay. So force due to the magnetic field is BQV. So the idea is these two forces are equal. So Fm equals Fe. Fm is BQ simple V. Fe is V over D into Q. So now on either sides, I can cancel the Q's. The Q here will cancel off with the Q here. So simple V equals capital V here over BD. That is what they have told you to prove. The speed of the particle will be V over B. Right? Then the next part. An experiment was carried out using similar apparatus. Show that V was about 3 into 10 to the power 7 meters per second. It's a piece of cake. You just have to substitute. V equals V over BD. V is 231. D is 5.5 10 to the power minus 4. D is 1.5 centimeters, which is 1.5 into 10 to the power minus 2 to convert centimeters to meters. Which is 2.8 into 10 to the power 7 meters per second. No need. The next one. When the electric field between the plates is switched off, the electrons move in a circular path of radius 39 centimeters. Of course, yes, we know that. The accepted value for the charge per unit mass of an electron is 1.8 into 10 to the power 11 coulombs per kilogram. Deduce whether the charge per unit mass of an electron calculated using data from this experiment is consistent with the accepted value. The D is given 5.5 into 10 to the power minus 4. So guys, we know we can use the equation. Maybe I can start from the very beginning. F equals ma. Now there's no electric field, only the magnetic field. So the F is BQE M into V square over R. So the V's on either side will cancel off. BQ equals MV over R square. Sorry, not R square, it's R, right? From where did I get it? R square. It's BQ equals MV over R. Guys, listen, look at this. We have to check what? Deduce whether the charge per unit mass of an electron calculated using this data is consistent with the accepted value. The accepted value is given 1.10 to the power 11. Charge per mass. Charge per unit mass means they are talking about Q over M. So I will get the Q over M subjected here. Q over M is V over BR. Am I right? So what is the V? 2.8 into 10 to the power 7. B is 5.5 into 10 to the power minus 4. The R is 39 centimeters, which is 0.39. Which is 1.305. Into 10 to the power 11 coulombs per kilogram. Okay, what are they saying? The accepted value for charge per unit mass of an electron is 1.8 into 10 to the power 11 coulombs per kilogram. We are getting 1.305 into 10 to the power 11 coulombs per.
Right.
So what do you think?
No.
Not consistent, because 1.3 to 1.8 is a significant difference. It's about 25% less actually. Yeah, so it's about less than, more than 25% different, right? So you can write a conclusion saying, no, it's not consistent. No, it is not consistent with the accepted value. Okay.
10% is acceptable.
Right, here's part B. In 1927, there's no exact percentage. I mean, it depends. If you feel like it's about a small difference, then you can say accepted. And they won't be very strict about that. It's about the conclusion, I mean, the calculation what you do, and which way you try to justify it. So if there's a difference of about 9 or 10%, a person can take it either way. One can say accepted because it's very close. One can say no, not accepted, it's different. So both are, they will mark correct for both. So you have done the working, the mark is given for that. Yeah, correct. In 1927, J.J. Thomson's son directed beams of electrons at thin films of metal. The photograph shows one of the patterns observed. Explain how this pattern changed scientists' understanding about the nature of electrons. This is not A2. This is an A special, yeah. So guys, this shows the diffraction of electrons, no? Which is a wave.
So his son didn't get his name. He got his father's name. Son only. He didn't get his own name.
Now this is the biggest problem you have, no?
Yes, sir.
Okay, you come up with a name and give it.
So that has happened a lot in history.
Yeah. All right. Explain how this pattern changed scientists' understanding about the nature of electrons, right? This is the diffraction of electrons. This is diffraction of electrons. Full stop. Diffraction is a wave nature or wave property. Diffraction is a wave property. Full stop. So it confirms electrons do have a wave nature. Electrons do have a wave nature. They do also behave as waves. They behave as particles and they also behave as waves.
So what's this chapter's name called, sir?
Not clear, your line is breaking. Can you please come again?
So I said, what's the name of this chapter?
This was done in particle physics. In AS levels, we have done. In wave particles, there was a topic, right? About photoelectric emission. Right. Guys, you can go for a break. See you in 15 minutes. Right, okay. Guys, then turn to question number 13. Question 13. The 13th one. Mass spectrometry is used to determine the masses of different isotopes of an element. Atoms of the isotope are ionized and accelerated. They pass through a velocity selector and into a region with a uniform magnetic field as shown. An ion accelerator uses an electron beam to ionize atoms of oxygen gas. The positive ions are then accelerated across a high potential difference between anode and the cathode, as shown in the diagram below. The cathode has a hole in it so that the accelerated ions may pass in a fine beam to the velocity selector. The electric field strength between the anode and the cathode is 7.5 into 10 to the power 5 volts per meter. Calculate the potential difference between the anode and cathode. So the electric field strength is given 7.5 into 10 to the power 5. You know the distance between the plates is 6 centimeters. So guys, E equals V over D. Electric field strength is 7.5 into 10 to the power 5. V over the D is 0.06 in meters, 6 centimeters. Cross multiply, you will get the potential difference between the plates. $45,000. $45,000. That is the potential difference between the anode and the cathode. The next one. A stationary oxygen ion is formed. A stationary oxygen ion is formed halfway between the anode and cathode with a charge of 1.6 into the power minus 19 coulomb. Show that the velocity of ion as it passes through the hole in the cathode is about 5 into 10 to the power 5 meters per second. Mass of oxygen ion is given. Can you give a try? A stationary oxygen ion is formed halfway between the anode and cathode. And the charge of the oxygen ion is given 1.6 into 10 to the power minus 19 coulomb. Show that the velocity of the ion as it passes through the hole in the cathode is 5 into 10 to the power 5 meters per second. Mass of oxygen is given 2.7 into 10 to the power 6, minus 26 kilogram. Now the oxygen they are talking is formed here, right? Correct? Magnetic flux or magnetic flux density. Remember? No, you want it in terms of SI units. You can take it from the equation F equals BIL. F is newtons, which is kgm is minus 2. I is amperes. Length L is meters. From there, you can get the SI in terms of SI units, the B. Then 5 will be B into A. That multiplied by square meters. Right. So guys, show that the velocity of the ion as it passes through the hole in the cathode is this much. A stationary oxygen is formed. Now, one way that I can do this is I will use F equals ma. Now we know the electric field strength. If I use F equals ma for this, for the particle, F is EQ, M into A. So A equals EQ over M. Acceleration equals E is 7.5 into 10 to the power 5. Into the charge is 1.6 into 10 to the power minus 19. Over the mass is 2.7 into 10 to the power minus 26. So this gives you the acceleration of the particle, which will be give me a minute. 4.444 recurring 10 to the power 12. This is the acceleration. Okay. Then the rest is too simple to see what is the velocity when it reaches here. Grade 9 physics. V square equals U square plus 2As. V square equals U square plus 2As. V is what I want. V square equals U is 0. Plus 2 into the acceleration is this 4.44 10 to the power 12 into the SCs. So guys, they are talking about now the midpoint. So the midpoint to the end of the plate, from here to here, it will be 3 centimeters. That is 0.03 meters. SC is 0.03 meters. And that gives you the V square, and get the square root of that. Now I'm getting 5.16 into 10 to the power 11 meters per second. Oh wait, where did I make the mistake? Hold on. No, not 11. 2 into 4.44 into 0.03 into 10 to the power 12, and get the square root of that answer. That is 5.16 into 10 to the power 5. Correct. Okay.
This is real.
Huh? No, just basics. Just basics. We just use F equals ma. You know the force is EQ, right?
Very hard to remember many equations and all.
That is physics.
So you should give us that booklet on the back. So
Yeah.
It will be anyway there. In the formula sheet, it will be there. But are you telling me that you don't know, you can't remember F equals ma?
So that-
Are you telling me that F equals EQ, you can't remember?
So I said like I forgot about that.
You forgot?
Yeah, and because equal is not.
So I
F equals EQ is hard. What? Are you kidding me?
So I used 21 some. I put F equals BQ V there.
How can a B be involved here? There's no magnetic field here.
That's what I put.
Okay. Right? Fine. Then the next part B. The oxygen ions enter the velocity selector. Now you understand, right? From here, guys, from here, ions are moving through this one, and then now they came out of the anode, sorry, the cathode, and then they enter into a new section, which is they have called the velocity selector section. So now we are getting into that. Oxygen ions enter the velocity selector with a range of velocities. The velocity selector allows ions with a specific velocity to travel in a straight line as shown. Plate P is a positive and plate Q is negative. Okay. So they are telling now there are oxygen ions entering into this region with different velocities. But ions with a specific velocity will just go undeviated. Correct? The other particles, depending on their velocity, they might either get attracted to the plate P or they might get attracted to the plate Q. Okay. Fine. The question is now, a uniform electric field between the plates acts on an oxygen ion. A uniform magnetic field acts so that the magnetic force on the oxygen ion is in the opposite direction to the electric field. Explain the direction of the magnetic field. I'll give you a minute, think about it.
So it should be in the upward direction, right?
Is it?
Yeah.
Let's see. Fine. Guys, now look at this one. Oxygen ion is positively charged. Listen to me, now stop your work. Oxygen ion is positively charged. Listen to me. So, the force on the oxygen ion due to the electric field is downwards. There is a force on the particle due to the electric field because it will get attracted towards the negative plate. Q is the negative plate, P is the positive plate. Am I right? So, which means force due to the magnetic field has to be upwards. Correct? No? That's what the question says. Force due to the magnetic field is in the opposite direction to the force due to the electric field. But the question didn't ask you which way is the force due to the magnetic field. The question is, explain the direction of the magnetic field. Which means, now guys, a positive charge is moving to the right means the current is this way. The force is upward. There comes Fleming's left-hand rule. FBI, force is up, current is this way means magnetic field has to be into the plane of the paper. Okay, so it's a 2 marker right under that. Force due to the electric field. Force due to the electric field. Force due to electric field on the particle is towards Q. Full stop. Force due to magnetic field is towards P. So the magnetic field is into the plane of the paper. Right. Is that okay? The next one. The velocity selector is used to produce a beam of oxygen ions traveling in a straight line with a speed of 5 into 10 to the power 5 meters per second. Calculate the magnetic flux density of the magnetic field that is required. The electric field strength between the plates is given 10,500 newtons per coulomb. Okay. So guys, the primary condition that is required for the particle to be moving in a straight line is the force due to the magnetic field and force due to the electric field should be equal and opposite in direction. Then only if you move in a straight line. Correct? So here we can take if M equals Fe, force due to the magnetic field, equal force due to the electric field. Force due to the magnetic field is BQV. Force due to the electric field is EQ. So the Q's on either sides will cancel off. So B is equal to E over V. E is 10,500. B is 5 into 10 to the power 5. .0.021 Tesla. Right? The next one. After passing through the velocity selector, a beam of oxygen ions with the same velocity, enters the region of uniform magnetic flux density. Different isotopes of oxygen can be present in the beam. Explain why the detector will only detect one particular isotope. As you can see the diagram, right? There is a uniform magnetic field. These particles which are coming straight will go through that and it will reach a detector. The question is now, after passing through the velocity selector, beam of oxygen ions with the same velocity, enters a region of uniform magnetic flux density. Different isotopes of oxygen can be present in the beam. Explain why the detector will only detect one particular isotope. First tell me, what are isotopes?
And then people say there is a particular number of neutrons.
Equal number of protons, different
And
number of
electrons, different number of neutrons.
equal number of protons, different number of neutrons. Am I right?
So that means
what
they will
can-
have different masses also.
the masses will be different.
Different. So the velocity
Right.
velocity also will be different.
The velocity is not different. Listen,
The
guys,
speed.
F equals ma. I'll start from this one. This is the third or fourth time I'm writing this today. F equals BQE, mv square over r. So the v and v will cancel off. R equals mv over bq. Okay. Now, if you take particles of different isotopes, they have the same speed. They're telling they are all moving at the same speed. They are in the same magnetic field. They have the same charge, but their masses are different. Okay, their masses are different. So their masses are different means their radius will be different. Okay, so the particles which has exactly the same radius as the radius of curvature of this thing that they have will only be detected by the detector. Understand? Those who have a different radius from what is required will end up somewhere else. Understood? So your explanation has to be, show this equation and then mention.
So, when experiment.
Yeah, show this working and then we have to show where the conclusion is this. The radius depends on the mass, velocity, the mass, speed, B and Q. Speed B and Q are equal, but mass is different. That is the core part, right? Different isotopes have different masses. Different isotopes have different masses. So their radius will be different. So their radius will be different. Full stop. Only the particles with the correct radius, will be detected by the detector.
And we see since each isotope has a different mass, the reflection due to magnetic field is different. So, only one particular reflection, one particular isotope will be going in the correct path to reflect.
Then you also have to mention, to be on the safe side, it's a 3 mark. B, B and Q are the same. You have to highlight on that. But when I come up with this equation, they know, the examiner knows that I have stated that B, B and Q are unchanged. Only the mass is changing. Okay.
That is copy pasted what I learned from chemistry. But here is the equation.
Better, safe. Right. So guys, that's it for the day. But you can mark a few more for homework, I guess.
So it went much faster than expected. Like it only felt like 1 minute.
Really? Guys, 15, give a try and see. I don't know whether you will be able to, but give a try and see. Hmm. Enough for now. We will do the rest on the next day. So we will continue from the next subtopic, the EMF induced in a coil, the next day. Bye, people. See you. Take care. Have a nice week ahead.
You said bye, all day.
See you. Take care.